Chapter 2 of this biology textbook is going to cover basically all the chemistry type things that we're going to go over for biology. It's a brief overview of chemistry. If you guys are taking chemistry, you're going to get kind of a double dose of this and a much more in-depth dose of this. So if you've already taken chemistry, this hopefully is just a review for you. If you're in the process of taking chemistry, this hopefully will give you a precursor for what you're going to learn there. So all organisms are composed of this stuff called matter, and matter is anything that takes up space and has mass. Mass is another term for weight, but mass, you have the same amount of mass whether you're in no gravity or gravity like we have here on Earth. Weight is a little bit differently. You'll have much lower weight if you go onto the moon because there's no gravity pushing you down, but your mass stays the same. So matter is anything that takes up space and has mass. And all matter is made up of elements. So rocks, although they're not living things, these are matter. Plastic is matter. Non-living and living things are all things that are matter. Elements are substances that you can't break down into smaller substances by chemical reaction. So they're the basic chemicals of our world. A compound is a substance that has two or more elements together or in some sort of a ratio. So compounds are multiple elements and an element is the single thing. And a compound has emergent properties, characteristics different from those of its elements. So if you think of salt, that's sodium chloride. Sodium and chloride have individual separate properties, but when together, those properties are different than they are as their individuals. We have 92 natural elements, 20 to 25% are considered essential, which means that we have to have them in order to live. And so these might be vitamins or minerals. They're things that we usually get through our diet. Sometimes they're things that you can get through your environment as well, through the atmosphere. Trace elements are required in very, very minute quantities. But if you don't have trace elements, then problems occur. So in humans, iodine is a trace element. If you don't get enough iodine, it causes goiter. And in the United States, one way to prevent that, so that we were able to get enough iodine, is that we started adding iodine to salt. So if you look at your can of salt, it says iodized salt. You can get iodized salt and non-iodized salt. But that was a simple way because it can't be tasted, it doesn't mess up the salt, that it prevented that deficiency that some Americans were having a long, long, long time ago. These are the elements that are essential to the human body. Most of our mass is made up of oxygen, carbon, hydrogen, and nitrogen. And the way to remember that is it's CHON, carbon, hydrogen, oxygen, nitrogen, CHON, C-H-O-N. So over 95% of our body mass is made up of these elements. Nitrogen is going to be found in our proteins. Hydrogen is just found everywhere. Carbon is what makes up organic beings, and we're an organic being. And then oxygen is mixed in there as well. The other elements that are found in our body, calcium, phosphorus, sodium, sulfur, chlorine, magnesium, these make up only about less than 4% of our body, but they're still a very important part of it. So I would definitely know the elements that make up the majority of the human body, being the CHON, carbon, hydrogen, oxygen, nitrogen. So some naturally occurring elements are toxic to organisms. In humans, arsenic is linked with many diseases and can be lethal. So sometimes elements aren't good. Some elements we have to have in order to survive, and some can actually kill us. Some species become adapted if they're in environments where there's a lot of toxic elements. They become adapted to that. So this is kind of a cool example. Sunflower plants, when they're in the ground, can take up lead and zinc and some other heavy metals that are usually lethal to most other organisms. And so scientists were able to utilize that and plant a bunch of sunflower plants to detoxify contaminated soils that arose after Hurricane Katrina, and water had run over areas that bringing toxic elements that weren't normally there. Each element consists of a certain type of atom. Atoms are the smallest unit of matter that still retains the properties of an element. And each element contains a certain type of atom different from the atoms of every other element. So atoms are unique to individual elements. The atoms that make up elements are made themselves up of three things. They have neutrons, protons, and electrons. Electrons are negatively charged. Think of electricity. And in ball and stick models, they'll show the electrons as little dots around the core or the center of the element. Well, in reality, electrons are constantly moving. And so they're more likely to be more of like a cloud. It's because they're so fast and moving all the time around them. In the center or the core of the element are your neutrons and your protons. Protons are positively charged, and neutrons have no charge. They're neutrally charged. So the neutron mass and the proton mass are identical, and they're measured in Daltons. So if you're told if you're given the neutron mass, then you'll automatically know your proton mass because it's identical. If you're given the total mass of an element and only giving the neutron mass, you can figure out the proton mass, right? Because it's identical. Atoms of the various elements differ in number of subatomic particles. So an element's atomic number is the number of protons in its nucleus. Its mass number is the sum of protons plus neutrons in the nucleus. Mass is how much it weighs. Atomic mass is the atom's total mass. Atomic mass is about the same as the mass number. We assume that they're the same. So atomic mass equals mass number equals protons plus neutrons. So if you're looking at sodium here, the way it's usually represented on top is our mass number. It's the number of protons plus the neutrons. The atomic number is what's down below. That's the number of protons, 11 for sodium. Well, 11 plus 11 is 22. Our mass number is 23, right? So that tells us that although we said that protons and neutrons are identical, it's not necessarily the case when you're adding the mass number. So in this case, if we're given the number of protons and we're given our mass number, we can assume that the number of neutrons we have is 12. So 11 plus 12 equals 23. Because neutrons and protons each have a mass of approximately 1 Dalton, we can estimate the atomic mass, the total mass of one atom of sodium, as 23 Daltons. All atoms of an element have the same number of protons, but their neutrons might be a little bit different. And so an isotope is where you have two atomic forms of the same element, but they have differing numbers of neutrons. And a lot of these isotopes can be radioactive, which means that they decay spontaneously. And when they do that, they'll give off particles of energy, which usually show up to us as light in some way. And we're able to utilize that using radioactive isotopes. So in an unstable element, you can inject it into the body, and we're able to identify a lot of medical disorders. In this case, it's throat cancer is shining in there. So they can trace these atoms through metabolic processes. They inject them into the body. They let them metabolize and break down, and they'll get stuck in places that are not supposed to be there and teach us different things. Energy is the capacity to cause change. These are all definitions that are important to understand and know. Potential energy is the energy that matter has because of its location or structure. So your potential energy would be a whole lot higher if you are standing on top at the edge of a cliff than if you're down at the bottom of that cliff, because your potential to fall off and give off heat and do damage is a lot higher up there than it is standing stable on the ground. So potential energy is the energy matter has because of its location or structure. So a round ball would have a lot more potential energy than a square ball because it's not going to move as easy, right? The electrons of an atom have potential energy due to their distance from the nucleus. Changes in potential energy occur in steps of fixed accounts. An electron's energy level is correlated with its average distance from the nucleus. And we'll talk about those shells and where the electrons sit. far from that nucleus. When we talk about thermodynamics, we'll get into more depth on what energy is or potential energy is. Electrons are found in different electron shells, and these shells are varying. They're like orbits outside of the nucleus. The energy level of each cell increases the distance from the nucleus, and electrons can move from higher to lower shells by absorbing or releasing energy. So in the image up there for the ball, that ball on the very top step has the highest potential energy, and as it bounces down, its potential energy is less and less, right? Because it's losing momentum, or it has less chance of gaining momentum because it's on lower steps. If you're looking at an atom, at an element, they have the atomic nucleus, which is in the center, and they have a greater potential energy on the outside than they do on the inside. So the first shell has the lowest energy level. It's like the lowest step for that little ball. The chemical behavior of an atom is determined by the distribution of electrons in electron shells. The periodic table of elements shows the electron distribution for each element. So if we look at this is a portion of our periodic table. You guys have probably seen a periodic table before. They're always in some sort of a science classroom, whether you're in one or you're seeing one on TV. But our periodic table is a list of all of the elements, and it shows us a lot of things. It shows us the atomic mass, it shows us the atomic number, but it also will give us the number of electrons. And so we can determine how interactive these, how strong, how much potential energy these elements have. And when we talk about potential energy, that might be the potential energy to bind with something else and make a new element. The chemical behavior of an atom is determined by the distribution of electrons in that electron shell. So if we look at the first shell, hydrogen only has the ability, because it only has one electron, to bind with one other thing. So it has a fairly low potential energy, right? But if you move over and you look at carbon, and by the way, these electrons have to be paired with one another. So helium only has helium has two. That means it can't pair with anything. It has a super low potential energy because it's already paired. Hydrogen is a single one. It wants to pair with something. But if you look over here at carbon, carbon has 4 unpaired electrons on that outer shell. That means it could potentially bind with 4 other things. So it has a very high potential energy. So looking at that first shell, hydrogen and helium only have electrons in the first shell. The first shell can only hold 2 electrons. The outer shells, every shell outside of that can hold 8 electrons. First shell holds 2, the rest can hold 8. So some elements have electrons in their second shell, and then some go as far as having a third shell. Chemical behavior of an atom depends mostly on the number of electrons in the outer shell. The outermost shell is called the valence shell, and the electrons that are in that valence shell are then called valence electrons. And how they react to other atoms is going to be because of which electrons are unpaired in that valence shell. These electrons, if you notice, even like with the third shell, there's 2 in magnesium. Magnesium has our 2 right here. Then it has, so because it has 2 paired here, we can now start filling up our second shell. 1 pair, 2 pair, 3 pair, and now 4 pair, right? Now these guys come out, and you notice that it doesn't pair up on the outside. You always will start, you do 1, 2, then this one would have gone 1, 2, 3, 4, and then it would start pairing itself on the outside. So they fill single spots and then start to pair themselves. Okay, So formation and function of molecules depend on this chemical bonding between the atoms, and it all really has to do with how many of those valence shells are open for them. So atoms with incomplete valence shells can share or transfer electrons with other atoms, and this usually results in some sort of a bond. Now they're connected to one another because they're either sharing electrons or there's some sort of a negative positive linkage between the two of them. A covalent bond is where you share valence electrons between two atoms. It's very, very strong, like a very, very strong handshake. In a covalent bond, the shared electrons count as part of each atom's valence shell. The two or more atoms can be held together, and that makes a molecule. A molecule is two elements together. So in example, you have, let me see if I have a better picture. Hydrogen atoms. Hydrogen, remember, only had one electron in its valence shell. Well, they are going to share their electrons to complete that, that first shell that only holds two. They're going to complete it and make hydrogen 2, H2. So the notation that we would use to show that these two guys are bonded together is H with a line in the middle and H. And this can be abbreviated further by saying H2 because there's two hydrogens. In a structural formula, a single bond is where one pair of electrons is shared, and that shows you a single bond or a single line. Sometimes there's a double bond, and that's where two pairs of electrons get shared with one another. And so you've got a double bond there, and so that would be like oxygen. So hydrogen, you only have two electrons being shared. It's a single bond. You only have one complete bond here, right? But in this case, with oxygen, we have two. Because each oxygen has two unpaired electrons that want to pair with one another. So it's a double bond. In the case of water, H2O, oxygen, since it has those two unpaired electrons, will share a single electron of hydrogen, but share it in two spots, making H2O, two hydrogens and one oxygen in a single bond with one another. Methane is a gas, and methane carbon has four unpaired electrons. When we talk about organic chemistry, or if you take organic chemistry, one thing that makes carbon so incredibly important is that it has the ability to bond with four different elements, and it makes it very, very versatile and very, very important in the chemistry world. So that's what you see there is the carbon is sharing that electron with four hydrogens. So it's four single bonds. CH4. And why you put, in this case of water, the H before the O, and in this case, the H after the C, it doesn't matter. It's kind of like when you have kids and you call one first before the other because it's just the way that it sounds good. There's no rhyme or reason really to that I'm aware of. Each atom can share valence electrons, has a bonding capacity, and the number of bonds that the atom can form. Bonding capacity, or valence, usually corresponds with the number of electrons required to complete the atom. Pure elements are composed of molecules of one type of atom, such as H2 and O2, but the molecules that have a combination of things, like H2O and CH4, they're called compounds. Atoms in a molecule attract electrons to varying degrees. Electronegativity is an atom's attraction for the electrons of a covalent bond. The more electronegative the atom, the more strongly it pulls its share of the electrons toward itself. So sometimes electronegativity is equal, and so it's an equal handshake and equal sharing. But most of the time, one atom yanks and pulls the electrons and takes more than its fair share. So it's not totally equal. It's pulling to one side or the other, and that's called electronegativity. When it's equal, the negative pull is equal, it's called a nonpolar covalent bond. If one atom is more electronegative and it takes more than its fair share of that negative electron it's sharing, it's called a polar covalent bond. Polar meaning, well, there's poles, right? Like on a magnet, you have a north and a south pole, a positive and a negative pole. Unequal sharing of electrons causes a partial positive from the guy that's giving up more than its fair share, or a partial negative from the guy that took more than its fair share for each atom or molecule. So let's watch this little video
A covalent bond is the sharing of a pair of outer shell electrons by two atoms. For example, each of these hydrogen atoms has one electron in its outer shell, but needs two electrons to complete its outer shell. If the two hydrogen atoms share electrons, they can both complete their outer shells. The shared pair of electrons constitutes a covalent bond, shown in shorthand as a line. The covalently bonded hydrogen atoms form a molecule of hydrogen gas. A molecule is defined as two or more atoms held together by covalent bonds. An oxygen atom needs two electrons to complete its outer shell. Two oxygen atoms can share two pairs of electrons. A molecule of oxygen gas is held together by a double covalent bond, two shared pairs of electrons. A carbon atom needs four electrons to complete its outer shell. It can share electrons with four hydrogen atoms, forming a methane molecule containing four single covalent bonds. Methane is a compound, a substance formed by the combination of two or more elements. We call methane natural gas. It is the fuel burned in gas stoves and furnaces. An oxygen atom needs two additional electrons to fill its outer shell. Thus it can form two single covalent bonds. An oxygen atom can share electrons with two hydrogen atoms, forming a molecule of water containing two single covalent bonds.
Atoms sometimes strip electrons from their bonding partners because they're a whole lot stronger. And an example is the transfer of an electron from sodium to chlorine. And so what that makes when they completely strip it, so a covalent bond is that one is tugging a little bit more. It's kind of like you're stealing a little bit more of the covers, right? But an ionic bond is they're totally taking the covers off of you. So they're stripping it from someone. And what that causes is a more positive and a more negative element. And that positive and that negativity form a bond. So for sodium and for chlorine, the sodium steals, or I'm sorry, the chlorine is stronger and the chlorine steals an electron from the sodium, making this chlorine more negative. Sodium now is more positive because it's lost an electron, it's lost a negative factor. And as a result, the positive and the negative form a bond. So a cation is a positively charged ion, that was sodium, and the anion is the negatively charged ion, that was the chlorine. An ionic bond is the reaction between the anion and the cation. And this isn't a super strong reaction because if you think about it, you can separate the sodium and the chlorine in water. When you're boiling water, you have a solid form that now is no longer in there. It's mixed up with the water. Compounds formed by ionic bonds are called ionic compounds or salts a lot of times. So we have our typical salt, such as sodium chloride, our table salt, and in nature it's found as crystals. So let's watch this video that kind of explains exactly what I just said, but hopefully in a different way so that you can visually see it as they do the animation.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion, in this case a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
And of course, that's what table salt in its crystal form looks like to us, but if you break it down, it's a bunch of sodium and chlorines all ionically bound to one another. Most of the strongest bonds in organisms are covalent bonds. So the strongest bond is covalent bond usually. But many large biological molecules are held in their functional form by weak bonds. And weak bonds are ionic bonds, hydrogen bonds, and then van der Waals interactions. We'll talk about those. But the thing about these weak bonds is that in massive numbers, these weak bonds are very, very strong. So the best example I can think of is a chain link fence. One, they're little diamonds, two diamonds stuck together, you could easily pull apart. But it's very, very difficult to pull an entire chain link fence apart, right? It's very, in numbers, there comes strength for these weaker ionic bonds or weaker bonds. So we talked about covalent bonds, we talked about ionic bonds. Hydrogen bonds form when a hydrogen atom covalently bonds to one electronegative atom and is also attracted to another electronegative atom. Hydrogen bonds only occur between hydrogen and something else. So in the case of water and ammonia, you have two, instead of it, this H2O is a covalent bond for this element, but now we're trying to make a compound, right? We're mixing these two things together. And so with water and ammonia, oxygen is pulling and it's a polar covalent bond, oxygen being the stronger, stealing some of the covers off of the hydrogen. So the hydrogen is positively charged now. In nitrogen, it's the same thing. Nitrogen is taking some of the, pulling more than its fair share of the electrons from the hydrogens, and now nitrogen is negative. And so the hydrogen bond forms between oxygen's hydrogen and nitrogen down here, because there's a positive and there's a negative force. In van der Waals forces, electrons may be distributed asymmetrically in molecules or atoms. The resulting regions of positive or negative charge enable all atoms and molecules to stick to one another. So van der Waals interactions mean that these elements are very sticky. These weak interactions occur only when atoms and molecules are very, very, very close together. They can't reach out very far and pull one another to each other. Collectively, the interactions are strong. Think about like the gecko's toe hairs and the wall surface. There's actually van der Waals interactions between the toe hairs of that gecko, although that's not actually very accurate, right? Because geckos don't have true hairs. And the wall surface, there's a positive negative that's making that gecko be able to stick to the wall. A molecule's shape is key to its function in the cell. And so molecular shape determines how biological molecules recognize and respond to one another. Biological molecules recognize and interact with each other with a specificity based on molecular shape. Molecules with similar shapes can have similar biological effects. I'm trying to get to a video I thought was in here. But if we look at shape and function, there's two different models, space filling and ball and stick model. So if we just look at oxygen or look at water, the way that it's shaped, it's not oxygen with two hydrogens sticking straight out from one another. They're kind of bent down. And that's because of the interactions between the electrons, between the hydrogen and the oxygen. And this shape that it makes it so that the oxygen is much more negative too. So shape also allows for it to be more interactive with other elements. It's not just the electrons, but also maybe the shape. And then the way that they bend, when you have many, many, many different elements making this giant compound, the way that they've bent and deformed and kind of twisted allow it to be able to attach to things a little bit differently. So while endorphin and morphine are two different things, endorphin is what our bodies give off to make us feel better. Morphine is something that we take to release pain, to trick our brain into thinking that we feel okay. Well, what attaches to cells in our brain when endorphins are released, because we do something that releases endorphins like exercise or other things that happen, that endorphin is released, it attaches to our brain feels good, we feel good, we aren't in pain. Morphine has the same part. Everything else is different, but it just has this one little tiny part that can attach to our brain and trick our brain into thinking it's endorphin. and doing the same things in our body to make us feel the way that we feel when we release endorphins. Okay, so a chemical reaction is when you make and break chemical bonds. And so what you start with are called the reactants, and what you end with are called the products. That's what you produce. So in the case of water, your reactants are two hydrogens and oxygens. And the reaction occurs, and what is produced are the water molecules. So water is the product, oxygen and hydrogen are the reactants. Photosynthesis is a chemical reaction that we are going to learn about later on, but it's what happens when plants use sunlight to make carbs, basically. So, and we consume those carbs. So what you see is CO2 and H2O, 6 carbon dioxides and 6 waters are your reactants. This is the reaction, and the products at the end are glucose and oxygen, glucose being a sugar. All chemical reactions are reversibles, so the products can go forward, and then they can go backwards also, forward and backwards reaction. And in fact, that's happening all the time usually. And so chemical equilibrium is reached when the forward and the reverse rates are equal. So when you've got, well, I guess like in this case, reactants and products, it's also going backwards. And so our products are turning back into reactants all the time. And when you hit equilibrium, it's equal on either side. Hydrogen bonding gives water properties that help make life possible on Earth. So water is extremely important. You always hear about people saying on the news that if you're able to find evidence that there was water on another planet, then that means there was life on that other planet, most likely. And that is absolutely true. So there's different reasons for that. We'll get into some of these, but organisms are made up mostly of water, and we also live in an environment dominated by water. Yes, we're landlocked here in Texas, well, in San Antonio, I suppose, but we require water in the form of rain. We require water in the form of just watering from wells, our plants. Otherwise, even a living thing can't survive unless it consumes water. So water is extremely important for life. If we did not have water, we couldn't survive. Water molecules are polar molecules. We showed pictures of that earlier, where oxygen has the partial negative charge. It's hogging a little bit more of the electron, and hydrogen has the positive charge. It's hogging a little bit more of the, it's giving up a little bit more of the electron. And so two water molecules, while the oxygen is covalently bound to the hydrogens, two water molecules are held together by a hydrogen bond, right? Because oxygen is a little bit negative and hydrogen is a little bit positive. And so you have this bonding among them, right? And because of the way that they hydrogen bond and covalent bond, there are 4 very important and emergent properties that contribute to sustainability for life. And I would absolutely know what these 4 are. Water is cohesive, meaning it's sticky. It likes to stick to one another. If you think about when you do the old experiment where you have a penny and you drop water onto the penny, little drops of water, and it will bubble up before it gets too big, before it spills over, it's because it likes to cling to itself. Beads of water, as it beads off of things or drips down a glass window, will try to scoop up and get close to one another. It's sticky. Water also allows us to moderate temperature. Water in areas that are found by the sea or major bodies of water, temperature doesn't fluctuate as much. In the desert, it's hot during the day, freezing cold at night. But around shores, port cities, their temperatures are relatively constant, even in the wintertime, even in the hot summertime. Water expands when it freezes, and water is a very, very versatile solvent, meaning that it can mix, anything can mix with it. It can mix up anything, table salt, sugar, it mixes it up, right? Breaks it down. So that first emergent property is cohesive behavior. The fact that they stick together is called cohesion. They're cohesive. Cohesion due to hydrogen bonding contributes to the transport of water and nutrients against gravity in plants. So if you ever wondered how on earth that gigantic oak tree that's outside is able to bring water from the ground all the way up to the tip top of its leaves and go up, even like think of pine trees and things that are, you know, seem to be 100 feet up in the air. How does water get all the way up to the top? Well, it's cohesion, and it's something specific called adhesion, where they cling, where they climb, they cling to another surface to kind of climb itself to the top. So let's watch this video about that.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
Surface tension is another um, thing that's related to cohesion, and this is the measure of how hard it is to break the surface of a liquid. Um, it's easy for somebody strong like us to break through the surface of liquid, but if you think of um, like a spider, for example, or a little insect, they don't break the surface tension. It's actually pretty strong because they don't weigh enough, and so they're able to run on top of that water. Another one of those elements is that there's moderation of temperature by water. So water absorbs heat from warmer air and releases that stored heat to the cooler air. Water can absorb or release a large amount of heat with only a slight change in its own temperature. So if we get a little bit more into it, kinetic energy is the energy of motion. Thermal energy is the measure of the total amount of kinetic energy due to molecular motion. And temperature represents the average kinetic energy of molecules. This slide, instead of going too in depth with some of this stuff, I would just kind of memorize these vocabulary terms. That would probably be where you would most likely see it. What I would know is that we use something called a calorie, and it's the amount of heat that's required to raise the temperature of a gallon of water by a degree Celsius. So when you look at calories inside your food, that's kind of the same thing, where it's the amount, whatever you consume gives you the amount of energy to do enough work to raise water by a degree Celsius. So we say that water has a really high specific heat, and that is the specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram to be changed by 1 degree Celsius. So it takes a lot of heat for water to do that. Water resists changing its temperature because of its very, very high specific heat. It actually takes quite a long time and a very high temperature for water to boil. However, other substances will boil within seconds. Like alcohol will boil half as fast as water takes to do it. So water has a very high specific heat. It takes it a lot of energy, requires a lot of energy to heat it up. And this high specific heat is because of the hydrogen bonding. So it's really, really hard to break all those hydrogen bonds and get the water boiling. When you break the hydrogen bonds, you turn it into steam, and that's where the boiling comes from, and you see the steam come out of it. It's changing form. A lot of heat is released when you break those hydrogen bonds. So the high specific heat of water keeps temperature from fluctuating within the limits that permit life. So if there's no water found on a planet, it's going to be super cold or super hot, and you're not going to be able to survive there. So if you know, even along the coast of California, you've got these coastal cities that are, you know, 72, 75, 73 on average. If the water temperature is 68, they're not really all that far off, but just inland, just a tad bit. Santa Ana has now increased its temperature 10 degrees more than the average down there on the coast. So it's quite a bit, 15 degrees or so higher than the Pacific Ocean is. And when you go even further into the inland, those temperatures are going to be quite a bit warmer. And of course, at nighttime when it cools down, they're going to get quite a bit cooler. Evaporation is the transformation from a substance from liquid to gas. So you have a glass of water that's sitting on your nightstand and you leave it there for weeks and weeks. It was full, and eventually you'll notice that it starts to disappear. It starts to evaporate, right? It goes up into the air. Heat of vaporization is the heat a liquid must absorb for 1 gram to be converted to gas. As liquid evaporates, its remaining surface cools, and this process is called evaporative cooling. And evaporative cooling of water helps stabilize temperatures in bodies of water and organisms. It actually, water takes a very, very long time to totally, completely evaporate off. If you had a glass of alcohol, rubbing alcohol, or hydrogen peroxide even maybe, but rubbing alcohol next to a glass of water, H2O, the alcohol would evaporate much faster than that water ever will. Ice also floats on water, and we know that, right? You make yourself an ice water, the ice is always on the top. Ice floats in liquid water because of the hydrogen bonds. So when it starts to freeze, the hydrogen bonds kind of separate and stretch out. When water is liquid, hydrogen bonds are a whole lot closer. When water, because of a hydrogen bonding, when water freezes, it expands. And that makes it less dense, and so it weighs less than the actual water does. If ice sank, then all the bodies of water would eventually freeze solid, because if ice got cold on the top, because the ambient air temperature is cold and the ice sank to the bottom, it is not only freezing at the bottom and freezing the water here, but this temperature is getting colder too. Eventually all the water would freeze. But the fact that water stays frozen up at the top only means that it kind of insulates this warm water underneath. And so you never have a lake generally freeze completely solid. And that makes life also possible on Earth. If it sunk, we wouldn't have life on Earth because everything at some point came from the water. Okay, water is also the solvent of life. A solution is a liquid of substances that have been homogenized or mixed together. A solvent is the dissolving agent. The solute is the substance that was dissolved. If it's an aqueous solution, water was the solvent. So sugar into tea, the solvent would be the tea or the water. The solute would be the sugar that's been put in there. It's dissolved in there. And water is super duper versatile as a solvent because it's polar, and so it can form hydrogen bonds with these other things really easily and dissolve them and make them homogenized where there's not a separation, it's mixed completely. When an ionic compound is dissolved in water, each ion is surrounded by a sphere of water, and so it makes this little hydration shell. So like in this case, chlorine and salt, they make these shells, preventing these two from being able to bond with one another again. So they can't come back together again because these waters have totally surrounded it and protected it from one another. Water can also dissolve compounds made of non-ionic polar molecules. Even larger polar molecules such as proteins can dissolve in water if they have enough of those negative regions for them. There's 2 terms that I would know about water as a solvent. So I would know what hydrophilic and hydrophobic mean. Philic means to love. So these guys love water. Hydrophilic substances want to be around water. They love to mix up. Hydrophobic, phobia, afraid of. Hydrophobic substances don't have an affinity to water. They don't like it. So you hear about oil and water. Oil is hydrophobic because it doesn't want to mix up with, it will not mix up with water. It will form little tiny balls but it will never completely mix. Most chemical reactions in organisms involve solutes that dissolve in water. That's why most of our body is made up of water, so these chemical reactions can occur. I'm going to skip through that. What I would also know, and I believe this is the last section here, is acids and bases. So an acid is something that has, let's just move, I want to show you something really fast. Okay, so an acid is something that has an increased amount of hydrogen ions. A basic solution is something that has an increased amount of hydroxide or OH ions. And if it's neutral, then it's somewhere in the middle. So our stomach has a ton of hydrogen ions in them. So if we move back up, so sometimes that hydrogen ion, the hydrogen all by itself, is transferred from one water molecule to the other. And what that leaves behind is a hydroxide ion, an oxygen and a hydrogen that were left without their other hydrogen buddy. The hydrogen binds to another water molecule, and so it makes H3O. And so we just use the term H to represent this H3O molecule, okay? So what happens is you have two hydrogen, two water molecules, and one of these guys comes off and goes to the other water molecule. And what you end up with is 3 hydrogens, or this is our what we call our H plus because there's an extra hydrogen. And then this is our hydroxide. So this guy makes things a basic solution, and this guy makes things an acidic solution. This dissociation is rare, it's reversible, but it's important for the chemistry of light because that hydrogen by itself and that OH by itself are super duper reactive, and that's what makes acids and bases. So acids have extra hydrogen concentration, and bases have a reduced amount of hydrogen concentrations. They have less of them. So super strong acids like hydrochloric acids will dissociate completely into hydrogen and chlorine in water. But then ammonia is kind of like a weak base, and it attracts a hydrogen ion so it'll make NH4, forms that ammonium instead. And it's a reversible reaction, of course, because it's going back and forth all the time. It's a very weak reaction, actually. Sodium hydroxide is a strong base, and so it will separate the sodium and the hydroxide completely. Weak acids act reversibly, and they'll accept. So if it's a weak acid or base, they'll give things back and forth. The other thing that I would understand, and we're not going to get into molarity and stuff like that, is just that you measure an acid and a base in something called a pH. It's the amount of hydrogen concentration that you have. So acidic solutions have pH values of less than 7, and a basic solution is greater than 7. So 8 to 14 or 7.1 to 14 is basic. Acid is 7 and below, 7 to 0 or to 1. Most things in our body are somewhere in the basic range. It's a 6 to an 8. When you throw up, let's see if it shows it in here, gastric juices, it burns, right? And if you get really sick and you have really bad stomach bug, you'll start to eat away at the your esophagus gets sore and it hurts, and that's because you're throwing up and it's very, very acidic. Things that are, and acidic things usually break things down. Battery acid, right? Very, very harmful. Coke, lemon juice, if you let your teeth sit in something like that, they'll eat away at it. A lot of our household cleaners have ammonia in them. They're kind of basic. Milk of magnesia. So milk of magnesia is something that you take when you have acid reflux, and that's to counteract the increasing acidity that's coming up into your stomach. So internal things remain close to a pH. Now we are able to use things called a buffer. Buffers are substances that minimize the changes of concentration of hydrogen or hydroxides in a solution. So most buffer solutions contain a weak acid and a corresponding base, and so they'll combine reversibly to fix whatever it is that it's. And looking at acidification and acid in our world. When we do certain activities, we harm the water quality because all that stuff gets run off into it. And so we end up increasing the acidity in the water. And as a result of that, it has negative impacts on sea life that's inside of those waters. And that will conclude chapter 2, which was all about chemistry for Biology 1406.